All right, so for E, which is the second set of notes, and this is combining random variables. So first video was on random variables, and this is combining. So we have a scenario here where it says let X and Y be two independent random variables with the following probability distribution. So here's variable X, and here's variable Y. So it says if we let S equal X plus Y, create the probability distribution below. So here's what this is saying. So we're going to have S, and then we're also going to have the probability of S. But we don't know what this is because we have to add these two together. So over here, I'm going to do a sample set, and I'm going to do the sample set of S and then the probability of S. Okay, so what our sample set would be is if S is X plus Y, then my first one is going to be 1 plus 5, which is 6. And then I have 2 plus 5, which is 7, and then 3 plus 5, which is 8. And then I go to the next one, and so I would have 11, 12, and 13. So that would be this probability distribution that I have up here. So 6, 7, 8, 11, 12, and 13. Okay, now the probability of this is going to be this value of 0.3, which is my 1, times the probability of my value of 5, which is 0.4. So this probability would be 0.12. And then I look at 2 and 5. So this probability would be hold on, where am I at? Yeah, 0.2 times 0.4. So this is going to be 0.08. And then I go to this one of 8. So it's going to be 0.5 times 0.4, so this is 0.2, and then I go here and I would have 0.3 times 0.6, so 0.18. Another 0.12, and then my last one, which would be 0.5 times 0.6, which is 0.3. So I can finish this distribution down here, and I would have 0.12, 0.8, 2, 1.8, 1, 2, and 0.3. So this would be my probability distribution when I take these two random variables and I add these up. So now it's saying, what is E of S? Now, remember, what this is saying is what is the mean of S, and we would look at this as the expected value of this random variable S. So if I look at my calculator here, if I want E of S, that's these values of S. So if I go into stat edit, I want to put these values in. So I have 6, 7, 8, 11, 12, and 13. And then the probability of that is going to be 0.12, 0.08, 0.2. Okay, so let me just make a little note here. So what I have is that my L1 is my S value, and my L2 is my P of S value. All right, that's what I have here. So now to get this value of E of S and to get this value of the standard deviation, I'm going to run my 1vars data, because this, even though it was two variables, now I turned it in, because I added it, I turned it into one variable data. So I go here back into stat, calc, 1var stats, and my list that I put it in was L1, and this list was L2. Okay, now if you remember, we did this in the first lesson. You don't have this mean that's listed like this. The mean is listed like this. And this is not how we report it when we're dealing with random variables. We would report it this way, but in the calculator, we see it as 10.2. So this value here is 10.2. And my standard deviation is S sub x, which is going to be 2.6. So this would be my mean and my standard deviation. So if I go in here, now it's saying what is the expected value of just my x variables, so just these variables. So if I go back in to my list here, I'm going to go up to the top of my list and just clear it. And then here, I'm just going to clear it because it's a small list, so it's easier to just clear it up at the top. 0.3, 0.2, 0.5. And now I run this. And what I get for just my x variable is 2.2, and my standard deviation is 0.872. Okay, and now I want the same thing. I want my expected value, or my mean, of just my y data, so these 2 points. So I'm going to do this one more time. Oops. And I have the values 5 and 10. And then over here I have the values 0.4 and 0.6. Okay, so this tells me that my mean is 8 and my standard deviation is 2.45. Okay, now here's something that we see when we do this, and that is I have my E of X data and my E of Y data, and if I add these two up, which is what I did to get all these values up here, I took the X values times the Y values, I get that this is 10.2. And if I plug this into my calculator, 0.872 plus 2.45, I get this value of 3.322. So what we see here is that when we added, my mean stayed the same, but my standard deviation did not. If I add these two up, I do not get the same standard deviation, but if I add these up, I do get the same standard deviation. And if you remember clear back in Unit 2, when we were dealing with two variable data, we looked at two variable data and we said if we add or subtract, that affects the mean, but it does not affect the standard deviation. The standard deviation only comes into play if we multiply or divide. And that's not what we did here. We added two random variables. So if we look down here, it says there's a shortcut for finding means and standard deviations without having to create a new distribution. So what we did up here is we created this new distribution, but what we see is if we would have found the mean of the first one and the mean of the second one, we could have added those up. And that's what this is saying. If X and Y are two independent random variables, then we can take these if we're going to add them together, and it's the same as E of X plus E of Y. And it's the same thing here if we subtract. I would have E of X minus E of Y. Now, what we see, though, is that it's not the same with our standard deviation. So if I took my standard deviation and I looked at this as, if I look at this as S squared, remember this is our variance. And if we look at this value, we're going to say the standard deviation in X that's squared, so the variance, plus the standard deviation in Y that's squared. And if we have this side where we're subtracting, I'm going to have standard deviation of X squared plus standard deviation of Y squared. Now, super important, this was not a typo. This is subtraction, this is addition. So for standard deviation, our formulas, whether we're adding or subtracting, are the same. Okay, so I'm adding here, even though this is subtracting two standard deviations. Okay, so with this pink up here, when we're adding, we see this, but let's check this formula now and see if we can get 2.6. So if I look at standard deviation of S, because this is what I'm looking for, my standard deviation of S, which is 2.6. Now I know it's going to be the standard deviation of X, so 872 squared, plus the standard deviation of Y, which is 2.45 squared. And I'm taking the square root of it because this is the standard deviation. If I didn't take the square root, it would be the variance. And let's plug this in the calculator, see what we get. So I take the square root of 0.872 squared plus 2.45 squared, and what I get is 2.600, which perfectly is what we wanted up here. So this value becomes 2.600. So we know that that works. Okay, so you can create a new sample set. We did that, and that's where these values came from. The problem is, it's just, there's so many steps here you can make a mistake. It's just much easier if you just do the individual random variables and then combine. Okay? All right, so let's look at this. So we did transformations of variables before. When we did this, we did this transformation. Hold on, I got extra paper here. We did these transformations where we looked at ln of our formula or log. And we did this when we were trying to create a better linear, or when linear was not a good alternative for analyzing our data. And we knew that we would have to do a transformation, so ln or log, if we saw a non-random scatter or if we saw a pattern in our residual plot. So that's when we did linear transformations in Unit 2, is when we saw a non-random pattern or we saw something in our residual plot that maybe looked like this, and so we knew that a linear model was not good, so we went in and we made some modifications, okay? So now what we're going to do is we're going to look at this data and we're going to see if we need to do any type of a linear transformation. So this says, the folks at Google decide to try a random salary assignment for their workers this year. They have the following probability distribution where X is salary. So we have these different salaries and we have this different probability here. So this is the probability of $50,000 salary and 60, 70, and so on, okay? And so just to check this, I have 4, 5, 6, 7, 8, 9, 1. So this probability all adds up to 1. So it says, what is the expected salary for a random Google employee? And then what is the standard deviation? So what I have here is if I want to know my mean, so my E of X data, this is going to be my mean, the expected salary. So expected, think about this, and remember E to the X is the same as U of X. What I'm going to do here is I'm going to take the salary that I have, 50,000, and I'm going to multiply this by 0.2. And then I take the next salary. And we did this in the last unit that we just had. This is not new. And then I do this last one, 80,000, and multiply this by 0.1. So if I look at what my mean is, really, I probably should have done this so I didn't have to. Okay, so this shows that the expected mean is $64,000. This would be my expected mean. So if you remember standard deviation, my formula for my standard deviation is going to be my value, which is 50,000, minus my mean, which is 64,000, this value squared, times the probability distribution of 0.2. And then I would do it again for the second one. And then I get up to the last one, which is going to be 80,000 minus 64,000 times the probability distribution of 0.1. Now, this is important. So these steps right here of this data that I showed, this is required on the AP free response, okay? So I know that you can plug this in your calculator and you can get an answer, but the reason why I wrote all of this out is because you'll be required to write it out on your free response. So if I solve this now, actually, hold on. I'm not going to spend the time plugging this in the calculator because I just realized I have that written down right here. So my standard deviation of this random variable X is going to be 9165.15. Now, I moved this to 15 cents because standard deviation is, it has a unit, and the unit in this case is going to be money. So what does this mean? If I look at this, it says the expected salary for a random Google employee, given these different raises, would be $64,000. And then the standard deviation tells us plus or minus $9,165 from the expected mean of 64. So there's a $9,100 swing around the expected mean of 64,000. Okay, so now this next part says, Google decides that everyone deserves a $500 bonus. Create a new probability distribution and find the expected value in standard deviation. So here's what I have. I have this new value here, which is x plus 500. That's what these values are, x plus 500. And now I want to know p of x plus 500. So if I create this new probability distribution, it's going to look like this: 50,500, and the probability stays the same, 0.2, and then 60,500 at 0.3, 70,500 at 0.4, and then 80,500 at 0.1. So this is my new probability distribution. So if I go and I plug this in my calculator, so I'm going to go back into Stat, Edit, and then let me put my values in: 50,000, 60,000, 70, and 80. And then I'm going to put my probabilities in at 0.2, 0.3, 0.4, and 0.1. So here are my probabilities. If I run this, and I know these are the values from the first one. If I run this, stat calc 1 vars, here's the data that I came up with a minute ago. So I had the average here at 64, and then I had the standard deviation at 9,165.15. Okay, so now I'm going to run this again using the same data. And so if I go into Edit, I'm going to go to this column right here, and I'm going to add $500 to each one of these. Sorry, let me get back in here. Each one of these values. So if I take this value here of $50,000, and I go back in here and rerun this, what I see now is that my mean, or my expected value, is going to be 64,500, but my standard deviation stays 9165.15. Okay, now, two things that we could think about as we do this. So the first one is if we're adding $500 to each one of these, all that means is that you're going to take your mean that you have up here and you're going to add $500 to it, right? Now, this shows the data, and that's what the purpose of this was, is to show the data. And again, like we talked about, if we're adding, nothing changes to our standard deviation. Okay, now that's what this little box says. If we add or subtract a value from the centers, which is mean and median, we see a value change, right? There is no value change in the variability, so range, IQR, or standard deviation, if we're adding or subtracting, okay? It also does not change the shape of the probability distribution. I didn't graph these, but if I did, the only thing that you would see with these two is that you would have a shift to the right, okay? All right, so let's look at this last part. It says Google now decides it will pay cash at the end of the year for the salary. They will give out $100 bills. Let X equal the number of $100 bills that they give out. Create a new probability distribution, use the bonus distribution, and find the expected value and standard deviation. Okay, so here's what I have. I have X plus 500, which is the payout with the bonus, but now I'm going to divide that by $100, because if X is the number of $100 bills, I have the new salary divided by 100, and that's going to be how many $100 bills I have. So because of that, the probability is going to be the same. So I have this probability, and now I'm going to divide this all by 100. So if I look at just the number of $100 bills I would have 505, and then 605, 705, and 805. That's how many $100 bills I would have, okay? So if I look at this value down here, which is the probability of this number here divided by 100, I'm going to take the value that I have on all of these, and I'm going to divide that all by 100. Okay. So if I've got these values, I'm dividing them by 100, it's going to be 0.002, 0.003, 0.004, and 0.001. So let me change this distribution that I have here now. And I would have 505. And then I'm going to change these. 3. All right. And then I'm going to run this. Okay. So here's what I have. I have x bar, which is u to the x, which is expected value of x, is now going to be 645. So 645 $100 bills. That makes a lot of sense. We take our mean up here, we divide by 100. Okay? So now my standard deviation of x becomes $91.65. Actually, hold on, it's not. It's going to be 91.6 bills. It's not money. It's going to be dollar bills. So what do we see? Exactly what we thought we would see when we are dividing. If you multiply or divide your probability statement, your standard deviation changes, right? So exactly the same thing that we saw earlier. It works with random variables and not just value amounts, okay? So what we have here, and that's all that this says, if x is a random variable and a and b are both constants. So what this looks like is if I have something like a plus b of whatever my new value is, so e to the x. And actually, I guess I can plug this down here. So a plus b to the x, standard deviation. This is going to be a plus b e to the x. So we add, and then we're going to multiply by whatever this value is. So here, this a value is going to be add or subtract, and this b value is going to be multiply or divide. All right? So what we see with our standard deviation is that the change in our standard deviation, and that's what this is, so this, we're just looking at change, is going to be the absolute value of b times the standard deviation of our random variable. And the reason why this absolute value is because we know that standard deviation is always positive. And we know it's always positive because what we say is that a value changes, or whatever their standard deviation is whatever that value is. So let's just say it's 91.6. It's 91.6 bills above or below the mean. If I go back to this one, I would have 91.6 bills. So my variation would be almost 92 bills from our mean value of 645. Okay. All right, so let's look at another example here. It says, depending on the attendance of a minor league baseball team, the number of hot dogs and sodas sold at a game is given by the following table. So what we have here are two random variables. We have one that I'm just going to say H for hot dogs, and one that's going to be S for soda. So if the profit on a hot dog is $1.50 and the profit on a soda is 75 cents, find the average profit on hot dogs and sodas per game. What is the standard deviation? So here's what they have. They have at a game, they sell 100 hot dogs. The probability of them selling 100 hot dogs is 0.05. The probability of selling 2,500 hot dogs is 0.2. So that's where these values come from, the probability of them selling these, and then our sodas sold. Okay, so if I want to know what is the mean, if I'm going to randomly select a day, so depending on attendance, if I'm going to randomly select a day, what does that look like in terms of how many hot dogs I'm going to sell? So if I want E of H, so the expected amount of hot dogs that I'm going to sell, what I have here is I'm going to just plug this in, and I'll have, let me clear this out real quick. Actually, you know what? Go ahead and pause the video and plug your data in really quick, and then we'll run these just to save time on the video. All right, so what I did is my L1 is hot dogs sold, my L2 is probability of hot dogs, my L3, I went ahead and made this soda, and my L4 is probability of selling those sodas. Okay, so the first one I want to know is the probability or the expected number of hot dogs that I'm going to sell. So I'm going to go back into Stat, Calc, 1var Stats. Hot dog is L1 and L2, and here's what I get. So the expected number of hot dogs I'm going to sell is 1,025 hot dogs. And my standard deviation of those hot dogs that I'm going to sell is 793. So an average random day, I'm going to sell 1,025 hot dogs plus or minus 793 hot dogs. Okay? Now let's do the same thing and get our sodas here. So I go into 1var Stats. This time I put my sodas in my L3 list and my soda probability in my L4 list. And if I run this, this tells me expected number of sodas I'm going to sell is 680, and the standard deviations of the sodas would be 476. That's crazy. I would think that they would sell more soda than hot dogs, but what do I know? Okay, so now let's go back up here, and it says, if the profit of hot dog is 150 and the profit of a soda is 75 cents, find the average profit dog on hot dogs and sodas per game. So here's what I have. I have the average profit is going to be the expected value of my hot dogs, and my hot dogs are $1.50, so $1.50 times my hot dogs, which would be $10.25, plus my sodas, which are 75 cents, and my average sodas are 680. So if I plug this in, oops, hold on. 1.5 times 1025 plus 0.75 times 680. All right, so what this tells me is that the average profit would be $2,047.50. That would be my average profit on a randomly selected day. Okay, now let's look at the standard deviation. So standard deviation of my profit is going to be, now remember I have this formula here that I have to use, which is going to be 1.5 times my hot dogs, 1025 squared, plus my probability of my sodas, sorry, my profit of my sodas times 680. Whoa, hold on. I'm doing the wrong value. I want standard deviation, so 793. And then 75 cents times 475. So my formula here, I didn't write it down. So this is going to be my change. So my change is my B value times my standard deviation of my hot dogs times my B value times my standard deviation of my sodas squared. Okay, so let me put this in real quick. Sorry, that's super sloppy, but I hope you're following me on this. So 1.5 times 793 squared plus 0.75 times 475 squared. And that's going to give me my standard deviation of my profit is $1,241.70. Okay, so if I do an interpret, it doesn't say to, but let's just go ahead and interpret this. We would say minor league game can expect, so this word expect here is important, to make a profit of $2,047.50 per game with a standard deviation of 1,241.70. That's really what we've calculated here. All right, flip it over. All right, so here's what we have. It says, suppose two pro bowlers, Larry and Sam, have the following distribution of scores. So here's Larry's average, his standard deviation per game. Here's Sam and his standard deviation. So we want to find each of the following. So what this looks like is the expected value of Larry plus the expected value of Sam. And remember, these are our means. So what we have is just 239 plus 244, and that would be 483. Okay, so standard deviation of the two. So standard deviation of Sam minus the standard deviation of Larry. Now here, when we have, oh, sorry, this is not standard deviation, it's mean. So we're going to subtract the two. So I would have 244 minus 239, and that would be 5. Okay, here's standard deviation. So standard deviation of Larry and Sam. So I have these values here of Larry and Sam. I have to add these up. So it's going to be the standard, or the square root of 10 squared plus 25 squared. That one I'm going to have to do here. So 10 squared, so 100, plus 25 squared is going to be 26.926. Okay, now I'm going to just go right down here to E really quick, because what we see is Larry plus Sam and Larry minus Sam. Remember that this is the same formula, whether I'm adding or subtracting, so it's going to be 26.926. No change. It's the same. All right, this next one is 3 times the standard deviation of Larry. So if I have this, it's going to be the square root of 3 times Larry, which is 10, squared, and there's no value over here for Sam. So if I plug this value in my calculator, 3 times 10 squared, it's going to be, oh, duh, that was dumb. This is going to be 30. And here's how I know that. So the square root of something squared, it's like saying this, 3 times 10 squared, all of this to the 1/2 power. So because this goes away, it's just 30. Okay, so last one, expected value of 4 plus 3 times Larry, which is 239. Now, this is not hard. What's hard is to just make sure you understand what formula to use when. So 721. Okay, one more problem and then we're done for today. So this says, actually, you know what? I'm going to let you solve this one because it's very similar to everything else that we've done today. So I'm going to let you solve this. I'm going to pause the video and then I'll come back in a minute with it all solved, and then you can check your answers. All right. Here are the solutions. So I'm just going to put this up here for a minute. You're going to notice that I scribbled out a little bit here on my justification. So I decided to change this. Instead of a randomly selected student, I said if many randomly selected students are selected from either campus, the difference in tuition, main minus rural, would average negative 9250. Okay? So how do we know that they're independent random variables? Knowing the amount M spent on tuition at the main campus does not help us predict the amount R spent on tuition of a randomly selected student at a rural campus. So main campus, rural campus, they don't impact each other. Okay? Standard deviation, so I use my formula. What does it mean? Interpretation. The difference in the amount spent between the main and rural student varies by 163 from the mean of negative 9250. So we need this varies, and we need varies from what? Varies from the mean.